So the plan for today is we're going to be doing a little bit of a deeper dive into some of the sections that we actually did talk about briefly yesterday. So again, this is the first time through a set of slides. Depending on how much people ask questions or not, we may end up running a little ahead. But the plan for the morning is to talk about using the TPM for machine authentication and attestation. So going into much more detail about some of the keys and structures that we talked about yesterday and trying to provide a little more context for when and how to use them. When I talk about some of the options that some of these keys have, we'll talk about what those are and why we want one or the other. Then we're going to talk about data protection and storage, where we're focused on the local protection and storage capabilities. I try to give intuitive titles here, which makes explaining things very hard. Then we're going to talk about a whole bunch of the miscellaneous features that the TPM has. This is probably when we're going to loop back and address Eno's questions from yesterday. We are going to talk about programming for the TPM. I will tell you now, it's going to be very high level because this is a topic in and of itself that is worthy of several days' use if we're actually going to try and do it. Nobody was interested in the lab, so you're not getting the detailed dive. But this will hopefully give you enough information for you to go and pursue it yourself if you're so inclined, or to give you an idea of what the gigantic challenges out there are. I'm hoping to spend a bunch of time this afternoon addressing your problems and use cases and questions. If you've got a half-baked idea for maybe I can use the TPM for this, maybe not, would it work, we can talk through that and give you a much more concrete idea of, given this use case, given this concept, what would I do? If all of you go silent, which I will complain about, then I will talk about the topic that I tend to use the TPM for most, which is virtualization, and that'll give you a more concrete, here's how the TPM fits into a real-world application. So, again, same rules as yesterday apply. If you get confused at any point, ask questions. I will be trying to monitor the chat actively. If it starts flashing and I don't notice somebody with a mic, please tell me. So, in this section, we're going to start by going back into PCRs and locality, which we touched on yesterday. We're going to get into a little more detail. I did preempt parts of this talk a little bit based on questions yesterday, so I do apologize in advance if this seems a little redundant. Then we're going to talk about attestation and machine authentication, which is the two use cases that we really use, in general, the signing spectrum of keys for. So, PCRs. We mentioned these yesterday. These are a series of 20-byte registers, which is to say they're as long as a SHA-1 hash, which is the default hash algorithm the TPM uses. The TPMs you're going to be running into the vast majority of the time have 24. They could theoretically have more. Nobody bothers to put them in. Very, very old TPMs may have 12. If I want to find out what the contents of a PCR are, they're all numbered, so they're 0 through 23. And usually if I'm going to try and pick some set of PCRs that I want, we call that a PCR selection. For once, it's actually an intuitive name, which is just saying I'm going to want to look at 0, 1, 2, and 15. And that's, they bitmap them. It's the world's most inefficient data structure. But you don't have to care about that right now. PCRs are used mostly to store system measurements, and we're going to talk a little bit about some of the other things we can do with them in this talk. On every single boot of the machine, all of the PCRs are reset to known values. These are almost always all zeros. A few of them can, in certain cases, be all ones. And it is important to note that these are not freely modifiable registers. There's no just write operation for them. They can only be modified using two operations, one of which is called extend and one of which is called reset. We're going to go into much more detail about what those do shortly. And the main property of these is that they're easy to verify. I mean, you can just say, is this equal to what I'm looking for? But computationally infeasible, given those operations, to set them to an arbitrary value if the machine is bad. So, The only way that you can add data to a PCR is with this TPM extend operation. So we've got some value in a PCR. Let's start with all zeros because that's where we always tend to start. We will extend the PCR with some lump of data y. I'm being arbitrary here. It's going to be 20 byte value. If you want to put a giant file into a PCR, hash the file, then extend it with the hash. So the TPM will then calculate the SHA-1 hash of that data y and x, which is to say the data that was already in the PCR. So it's combining the old and the new data, and then it overwrites what's in the PCR now with that combined hash. So now I can extend it again, and now I've got the hash of A and the hash of Y and X. I can extend it again, get the hash of B and the hash of A and Y and X. So this is called a hash chain, where a verifier who knows A and B and X and Y and the order in which they were extended, this is important, can pretty easily just run a series of SHA-1 hashes and check to make sure it's correct. If you want to get to some arbitrary value, starting from a different initial value, whether that be you're trying, somebody has already extended a PCR with some completely unrelated thing, calculating a series of extends that will get you to the same endpoint is really not computationally possible. That's not an operation that Mercer can perform, which means that as long as the PCR has been extended at least once, getting to a different destination is extremely difficult. Now, I will note here that if a PCR is 0 and you expect it to be extended with some value y, and for some reason somebody had, things have gone bad, but that PCR has not been extended yet, you can still extend it with y. It's very important to check all of the links in the chain to make sure that something in the middle didn't say, when I said the chain here, I don't actually mean hash chain, I mean boot chain. So if the BIOS is bad, or the bootloader is bad, and the bootloader measures the OS, if a good bootloader measures a good OS, it is computationally infeasible for a bad OS to change its own measurement to look good. That's the main point of these PCRs. If the bootloader is bad, it can ignore the bad OS that's sitting there and extend it with the hash of a good OS if it knows what that looks like. And that's not hard at all, which is why we can't just say, oh, we'll just check the hash of the OS because that's the only one we care about. We need to look at what's putting that in there, because the hash chain is still reliable, but the source of information may not be. And this is why we care about the root of trust being accurate, and this is why we care about each step in that chain being verified. We can't jump over any of them without losing our assurance. So some, but not all, PCRs, and we're going to get to which ones those are and why, are what's called resettable. And this means that at any point during the machine's boot cycle, or in some cases during a specific point in the machine's runtime, you can execute a PCR reset command, which for the resettable PCRs will set it back to either all zeros or all ones. And there's a couple of PCRs which, according to the spec, may be all zeros or all ones, depending on, for example, whether the DRTM is executed. That's a level of detail we're not going to get into right now. The important part is that resettable PCRs do go back to a known state, and we generally can't tell whether a PCR has been reset or not. Even the one that resets different values, that generally, it's rare, it's not well defined as to which ones will go back to which. So, in general, assume that if it's a resettable PCR, you cannot detect whether it has changed, whether it has ever been reset. You're not getting history from boot. You can't even tell whether you're getting history from boot. So whether a particular PCR is resettable or not, this is defined by number. Remember how I said PCRs are indexed by number. So for example, PCR 0 is never resettable, PCR 15 is freely resettable. And that's going to be true for any TPM that meets what's called the PC client spec. The TPM spec just says there exist resettable and non-resettable PCRs. This is what it means. The PC client spec is the one that actually defines for real-world TPMs what's what. Now, I mention that in particular because theoretically there could be other TPM specifications. And a virtual TPM, for example, may have a specification eventually, which might say PCR 28 or 30, because it's a virtual world, we can have more memory pretty cheaply, may have a completely different set of permissions, and theoretically the virtual TPM spec could, if they didn't care about compatibility, change the settings on 0 through 23. So reset and extend, to be perfectly honest, both of these require appropriate permissions based on locality. So that's what we're going to talk about next. So in theory, there are 5 distinct localities within a TPM. You've got the trusted hardware, which is to say the dynamic proof of trust for measurement. The way this works is that there's this tiny little piece of CPU firmware that then measures a slightly larger set of measurement code. And then that goes into what the user provided it. So you are technically measuring the DRTM adjunct and then going on to measure whatever the code the user provided, which is that locality 3. Why they call that auxiliary components, I couldn't tell you. That's what's in David Grohrock's book on the subject, and he's the authority. Locality 2 is supposed to be the trusted operating system. Locality 1 are trusted applications, and locality 0 is the static root of trust for measurement, and what's called legacy, which is to say they didn't want to change the behavior expectations of those low PCRs from the original set, because legacy applications might have their own ideas about how they were to be used. Is it 12 or 16 course? I typoed, and I read the typo and I didn't notice. So in practice, we don't really have 5 different sets of permissions here. There is still, the trusted hardware on the DRTM is still distinct from the software that is launched by the DRTM. After we pass out of CPU-controlled code, we do in fact have an automatic locality change from 4 to 3. When we go into that CPU secure mode, we automatically go into locality 4. So locality 4 is by far the most reliable and specified of these, because it really has to do with the CPU's operation. We run a specific command, we go into locality 4, it passes control, we go into locality 3. Locality 3 is that software that we provided to the DRTM. You may remember yesterday we said you handed it some region of memory, and then control was passed to a place in that region of memory. This is what locality that region of memory starts operating in. When you leave secure mode, or when you start turning features back on, because technically you can not depart secure mode while nevertheless leaving secure mode. It's technicality. There's a command that automatically just throws you back into normal operation and returns to whatever you were doing before you started secure mode. That is distinct from saying, well, we entered secure mode, we're never going back, but we're going to turn back on things like multi-threading and memory access and so forth. So when you start turning things back on, you get into the OS portion of the program. Now the thing is, the TPM driver, whether it's controlled by the OS or separate piece of software, is pretty much what determines whether you're operating in locality 2 or locality 1. There is no way for the TPM to determine who originated a command. So each command to the TPM is tagged with locality automatically. And that locality, when it comes to 2 through 0, is based on flags on the memory that executed the command, which ends up being the TPM driver at the point that the TPM can detect it. So even though the ideal behavior we would like from locality is to say, these pages of memory that are owned by this application, so you have Firefox or my keychain manager are flagged with, this is a locality 1 application. And anytime that that process performed a TPM operation, it would automatically be open. That's unfortunately not actually the way it works. That would be the right way to do it, but it isn't the way they did it, probably because that was really infeasible, because you've got a driver that's actually the one executing all the commands. So what we're effectively saying is that the OS can decide whether localities 2 or 1 will be used, and it can basically set those flags on regions of memory controlled by the TPM driver, which can then decide for any given command, is this locality 0, 1, or 2. The default locality is locality 0. So even though it says this is the SRTM locality, really, if you aren't thinking about locality and you're not using the DRTM, you're in locality 0. You have to go out of your way to use locality 2 or locality 1. So we can use this to establish finer-grained control. Then all commands have equal permissions, but you have to trust your TPM driver, and it's not nearly as fine-grained as we might like. So, I said before, I don't know, can you guys on the remote actually read the numbers here at all? Or is this type too small? Okay, great. So, this here is a chart straight out of the PC client specification. If you're having trouble reading any of this and you want to know what I'm talking about, just let me know and I'll read some of this out more. This is the chart of permissions for various PCRs. And you can see here that all of the old school PCRs, 0 through 15, the ones that existed in the original TPM, are all identical. You can never reset any of them, and anyone can extend them. There are no permissions really on that. It's just not resettable, extendable. So these are great places to put things that are part of your system history. Two of these PCRs, 16 and 23, are universally resettable and universally extendable. And you may say, what on earth is that for? We can't rely on any data. There's not any kind of hash chain we can really build there. I'm going to talk about why those are tremendously useful PCRs to have around in a little while. The short answer is, if I want to put session data into a PCR, that's the place to do it. I want a single operation to be temporarily confirmable with the expectation that it will be white, because I don't care. Then we have a whole bunch of special PCRs, 17 through 22, which have various levels of resettable and extendable by various localities. Unfortunately, these are not necessary. This is a pretty arbitrary set of permissions. The localities that have PCR reset for locality 4, so 17 through 20 there, are all automatically reset whenever we enter the DRTM. So the DRTM just goes through and wipes those so that we can then reconstruct things as part of our trusted operating system boot or part of our Flickr application execution. So those are, actually I'm not sure if 20 counts there, I'll have to look that up. Certainly 17 through 19 have this property. Locality 4 automatically clears them, period. Then we have various tiers of permissions for what is allowed to extend it again. And locality 4 will always extend PCR 17 with its own measurements and the measurement of locality 3, and then 18 and 19 are, technically they call this locality 3 versus locality 2, but you will note locality 2 and locality 3 can extend both of these. I don't know why they decided to name some of these things what they did, because really, most of those names are nonsense. Even the thing that says trusted OS control, the OS has control over locality 2, that's true, but really, the OS gave that control to the driver, so how much do you trust your driver? I mean, theoretically, it could maintain that control itself, but now you've basically got your own. the OS has a distinct TPM driver from the rest of the system. That's not realistically an architecture I would expect to see frequently. So the main reason I pulled this up is that if you want to start playing games with locality with permissions, where you want to say that I have an application or a virtual machine or a subset of my operating system that I want to have privileged permissions, that I want to say it can extend PCRs and nothing else can. You don't get an arbitrary choice, at least not now. TPM 2.0, you're going to get arbitrary choices. TPM 2.0, you can start saying, this PCR has the following extend permissions, and I can set them to whatever I want. That's 2.0. 1.2, we're stuck with this chart. So if you want to play fancy games with permission, you've got a very limited window. You're pretty much in the 17 through 22 range, and let's just say you're not using 17 at all. That's the DRTM's special little playground. And if you want to do that, you refer to this chart and you say, okay, therefore I'm going to need to use locality 2, or I'm going to use locality 1, and I need to guarantee as part of my system design that locality 2 isn't being used in certain fashions, because very few of these have only one region that has permissions, and we're kind of stuck. There's no such thing as a locality that is completely non-resettable, but has permissions that are limited. So, pros and cons, yes, there is theoretically permission infrastructure. Yes, you can wedge certain use cases into it if you kick hard enough, but it is not really designed for arbitrary flexibility. We're going to get that in a couple of years when 2.0 comes out. So the problem with PCRs is that these nice hash chains that make them easy to verify and hard to forge are also extremely fragile. Because absolutely anything will change the hash unpredictably. As Ina pointed out yesterday, if you change a timestamp in a file, well, that changes the hash, and we can't tell if that was a timestamp change or a rootkit. So predicting what those hash values is sort of what we call the holy grail of measurement here. There's a whole bunch of researchers trying desperately to get golden values that we can predict in advance. Unfortunately, that's easier said than done. So there is some research into what's called property-based attestation, where I want to associate a given measurement with properties about the system rather than with the hash. Most of those today are pretty primitive. They're things like, I have a list of golden hashes, all of which I promise have the property, this is a good OS. And what goes into the PCR is, this is a good OS, not an individual hash value, but you're still doing a lookup on a table from some set of arbitrary hashes. That really isn't very helpful. Or we're looking at, you've got a trusted measurement agent, where you measure the agent with a hash, and the agent tries to give you a more intelligent response. In that case, what's extended is still 20 bytes, but at least at some level, somebody has tried to give you something a little more detailed. But realistically, other than good or bad, 20 bytes is a little hard to do. So what we'll often see there is you have a hash of a report. The hash is in the PCR. The report itself gives you the human-readable data that says yay, nay. So we're not there yet. We're working on it. From the industry side, they are trying to do things like standardize BIOS measurements and the operations that the BIOS does when extended PCRs. It's still useful. We can still make use of it. But we're mostly looking at very constrained cases where we're trying to do change detection or we're trying to map against a very limited set of good values. This is part of why all those people who say, well, Disney's going to spy on me are on crack, because if you think it's hard in an enterprise environment where we've generally got one corporate image that contains a limited number of variations, and we're all supposed to be reasonably up to date on our patches, and we all have limited set of hardware, in that world, we still cannot today reliably identify is that good or not. Trying to do that in a a consumer environment where maybe you're running Windows 7 and maybe you're running Windows 3.1. No, this is just not happening. So we're working on it. This is not a magic bullet.